So first, we have CS server, and in CS server, so to first access CS server, many of you that have taken CSO1 probably already know this, but it's simply you just SSH into like you type SSH and then your computing ID at portal.cs.virginia.edu into your terminal, and that will take you to the CS server. And that will take you into a CPU where you can perform like quick and simple CPU related tasks. What we're going to be focusing on here is mostly the GPU server. The way you would get into that is you SSH into your computing ID at GPU server. The 01 can be changed with anything from 01 to 19 based on which GPU server you're in, based on which GPU server you want to go to. Each GPU server, most of them have 4 GPUs available except for GPU server number 3. And most of them run 2080s except for GPU servers 9 to 16, which has RTX 4000s instead. And so you would get into it by like SSH GPU server 01, and then the -J stands for jump, uh, because you're jumping from like your computing ID at portal.cs.virginia.edu over to the GPU server. This is basically a shorthand for simply starting with an SSH into your portal and then going to like, and then SSHing into the GPU server. The -J is just like a faster version of doing that. I can also display it right here. So, sorry, did I stop? Oh, okay. So we can just SSH into your portal. And this gets you into CS portal. And then from there, you can SSH into a GPU server. And you're into a GPU server. GPU server 1 has, oh yeah, sure. GPU server 1 has, in this case, 2080s, 4 of them. And you can use those for running quick and simple tasks which require a GPU. So now, going back to our presentation here. Next, once you get into CS server, you might notice that you can't really run any Python scripts or do anything because you haven't loaded any modules yet. So module is short, ML is short for module, and module and ML in the terminal can be used interchangeably here. So ML avail is probably the first command you might want to run. That shows you all the modules that can be loaded right from the get-go. So in my case, if I were to do that, ML avail here, it would show me all the modules that are available. There's quite a few. I'm not going to really go through them here, but you can also do ML list to see the modules that you currently have loaded. In my case, I have these modules loaded right now. And right now I cannot run a simple Python script because I do not have Python loaded. So one of the first steps you might want to do here is to obviously load Python. However, to load, one of the things that Python has is a module dependency. This is where a module is required to load the module Python. So in my case, if you wanted to check what modules you need to load Python, you can always do module spider Python, which will show you that you need, well, first it'll show you all of the Python versions available. And one example you could do is module spider Python 3.12.3. In my case, I'm going to do Python 3.10 just for an example. So module spider Python 3.10.4. and you need GCC core 11.3. So if I do ml avail Python, this will show you all of the Python modules that are available for the GCC core, which I have installed right now. Right now, I have GCC core 12.2.0. So the Python version that works for this GCC core is Python 3.10.8. Of course, you could always ML unload and then take out this GCC core, replace it with a more recent GCC core like GCC core 13, and then load a more recent version of Python like Python 3.12. But I'm not going to do that right now, just because for the sake of loading Python, I'll just go with this. So ml load Python 3.10.8, and now we have Python. So if we go into ml list, we now have Python over here at number 26. So module spider shows you the module's dependencies, and it also shows you a brief description of each module. And then module load will actually load the module that you need. Now that I have loaded Python, I can run basic scripts like hello world or something like that. ML unload simply unloads a module. So for example, if you've loaded like conflicting versions of GCC, like GCC 11, GCC 13, and something like that, you can always unload one of the GCCs by just typing ML unload, and you've unloaded the module. ML purge simply unloads all modules that are currently there, and it'll let you just like kind of restart from base. And ML list shows you the list of the modules that you currently have loaded. So that's module commands. Next is NVIDIA SMI. This is a command in and of itself, and it shows you the available GPUs and the processes that are being run on each GPU. So if I go back here, and then I type NVIDIA SMI, we can see that there are currently 4 GPUs within GPU server 1, and all of these GPUs are 2080s. You can also see the process that's currently being run right now. GPU 0 is currently occupied by this process right here. And you can see that it's using about this much memory. So another really important thing that NVIDIA SMI shows you is the CUDA version. And the CUDA version is important because say you wanted to run like some kind of model, right? And say you had like some PyTorch version to run this model. Well, this CUDA version is important to know because different versions of CUDA are compatible with different versions of Python and PyTorch. So CUDA version 12.4 here is compatible with Python of anything greater than 3.9 and PyTorch 2.6. If you have a model that's running on like PyTorch 2.4, for example, then you might need a different like CUDA version here, like 12.1. You can also see the processing being run on each GPU. So over here, if you go back to NVIDIA SMI, you'll see that you have a PID for each process. So if I were to run a basic script, so first, let me just simply let me just load module miniforge. So ml load miniforge. This is a module that you'll need to activate a environment, like a conda environment. So now I can do conda activate torch environment. And I've activated my environment. And now from here, I can run a simple Python script that I made called python GPU loop.py. This is just a very simple script that basically puts it's basically an infinite loop here. So once I run this file, it'll just like take GPU 1 and it'll put it in an infinite loop. It'll just run unless I kill it, obviously. But now this is running. So if I go here and I type NVIDIA SMI, you can see that GPU 1 is being used by a Python script, which I have just run over here. So you can also kill this process. You can kill this process here just by typing Control C. You can also do it over here by copying the PID and doing kill -9 and then the PID. That's killing by PID. You can do that, or for simplicity's sake, you can just do Control C here, and you've canceled the process. So that's a very simple way to just kind of figure out like what process is running. And then this ps-p PID here is something to see like what argument was used to run like a specific process. So for example, if I go back here and then I do this Python GPU loop, and then I do ps-p, hold on, the argument changed. So I have to go back and type NVIDIA SMI again. And then if I copy this PID here, and then I do ps-p this -o args, you get the command, and which is python gpu loop.py, which I use to run that. So you can use that to figure out which thing you ran, and you can easily just kill it from there based on the process ID. So that's just an easy way to check like which thing is yours, like which program yours is running based on the PID. And if you need to like stop a certain program for whatever reason, you can stop like that. Next comes tmux, which is a it's essentially a terminal multiplexer. So what this does is even if you close your main terminal, or even if you're like logged out due to inactivity from your from your SSH session, the tmux session will persist. So over here, if I have like, I'm gonna first check if I have tmux loaded. I do not. So you need to always module load tmux first before using it. And then from here, you can create a tmux session. The commands for making a tmux session are right here, like create tmux session, detach, reattach. I'll show all of what all of these things mean right now. So starting with tmux new -s, and then the session name, I'll just make it Ani. This creates a terminal where even if you like detach from this terminal by doing Control BD, this terminal is still running in the background. And even if you get kicked out of your current SSH session, like even if you exited all the way out of this, you can come back to it, come back to GPU server 1, and you'll see that tmux session is still there. So this tmux session can be useful when you're running scripts that take like 3 hours. And if you get kicked out of your SSH session due to like inactivity or something, or if you need to close your laptop and go somewhere else, you can have your code still running within a tmux session. However, it's not advised to train like a model overnight on a tmux session because these processes can still be canceled by like uh, UVA themselves, or like if they see you're hogging like a certain GPU for too long, they might like just just straight up like cancel it. There are some protections against that. So basically, UVA does not recommend using tmux for like training GPUs overnight. And if I want to see the tmux session that I've just activated, you can always do tmux list sessions. And I have one tmux session with my name. And I can always go back to this tmux session by typing tmux attach session -t and then Ani. This is the longhand. There are shorthands for each of these commands. The shorthand for this would be like a-ses. But that would get you into the tmux from there. And then from here, you can basically run any program you want. And this program will persist even after you close your main terminal. So tmux can be useful in that sense. So if I were to run my Python GPU loop, I would first have to reload modules. So first, I would need to reload Python 3.8. So now I've loaded Python, and from here I can activate my Conda environment. Oh, right, okay. Sorry. Let me detach from this tmux session real quick. But basically, the point is uh you can run programs and you can have these tmux sessions running in the background. And if you want to kill a tmux session, you can do tmux kill session dash t and then your session name. So in this case, Ani. And then you can do tmux list sessions. And you'll see that there's no servers running. So that's the basics of tmux. You can create tmux sessions, you can delete them, you can have them running certain processes, and that's kind of it. And these processes will persist even after you close your main terminal. And then you can split your tmux into panes as well. Panes just means like it'll split it like horizontally or vertically. So for example, if I wanted to split my tmux session horizontally, I could first recreate my tmux session, and then I could do Control B and then percent sign, and that'll split it horizontally. And then if you want to like split it vertically, you could always do Control B and then this like quotation, like the double quotation. And if you want to kill these panes, you can do Control B X and then yes, Control B X, yes, and that'll get you back to the normal tmux session. And then if you want to kill all tmux sessions, you can do tmux kill server. And that'll just kill all tmux sessions currently running. Tmux is useful for mostly for interactive tasks. That'll take a couple hours. Like for example, if you're running a script and you need to constantly check the output, like say you're printing stuff into your terminal, and you want to see what that terminal like, and you want to see like the stuff being printed into your terminal, you can always run it like through a tmux session. And the tmux cheat sheet is linked here. This is a simple like list of all the tmux commands that are available to you. And there's quite a few commands that I've not covered in this, but you can feel free to look at those yourself and go from there. So next is Rivanna. So Rivanna is basically a high performance computing system which allows you to access like quite a few GPUs, and you can basically do like large like tasks, sort of like training a model or uh, working on like huge computations, stuff like that, basically. Um, so the things I'm going to cover regarding Rivanna are everything that's been circled here. So like the Scratch directory, home directory, your jobs, the code server, and your interactive sessions. So first, Scratch versus home directory. Uh, Files in your Scratch directory get deleted after 90 days. So that's something to keep in mind when you're working there. Uh, Meanwhile, files in your home directory never get deleted. Your Scratch storage has 10 terabytes, while your home storage has 200 gigabytes. So Scratch is best for storing large models here, and home is like best for storing the results of those models. So for example, if you need like evaluation metrics on like 20 models, and each of these models is pretty big, you could always put your models in the Scratch directory, and then take your evaluation metrics and have them be stored in the home directory. This is just a simple example on how you would store things. And if, for example, you need these models later, you can always uh, you can always upload them to your own uh to your own devices and store them locally if you wish. So next is code server. So if I go into Rivanna right now, let's first escape out of this. And if I go into Rivanna here, right now I have some code servers running. These are the code servers from ML at UVA. But basically, this is the screen that you would see if you clicked on code server by going into interactive apps and then code server. You can see that you can choose an interactive code server, which is simply just it'll give you this like CPU cores, and you can run basic scripts on a VS Code like interface. That interface looks like this. Once you get into like your session, it's just your home directory and then everything you have. But over here, you can choose interactive or you can choose GPU. You can choose your number of hours, the number of cores you need, the allocation. In this case, the allocation you'll most likely be using is ML at UVA. I have some other allocations here, which are specific to like professors because I do research under them. But if you're working for like an ML at UVA project, if you're working on an IP or something like that, then you will most likely be using this, the ML at UVA allocation. And then you can choose the GPU that you want. Default just means go with whatever is first available. But otherwise, um, you can choose like an NVIDIA A100, A6000, B100, or A40. You can choose the number of GPUs that you want as well, and then you can launch your session. I already have a session launched, so I won't be launching another one. But for now, you can connect to VS Code and you will get what looks like this. Basically, Rivanna, but like a VS Code interface to work on. So that is code server. From there, uh, you can move on to Slurm, which by far is the best option for training models overnight here. If you want to train like or do some kind of computationally intensive task that requires either a lot of time or many GPUs or both, uh, Slurm is your best option. It's basically a workload manager, and it allows you to customize your job script to quite the degree. So I'll be going over what all of this means pretty soon, but just to let you know beforehand, this slide, the picture in this slide and the picture in this slide are exactly the same. The only real difference is right here, it's like sbatch-a ML at UVA. Um, I have sbatch-account. These are just the long forms of like the shortcuts that you can use. I'm going to be referring to this image more often just because you can kind of understand uh, what each part means. But yeah. So this right here is a simple Slurm file, which runs hello world.py. And hello world.py is just hello world. Nothing special there. In fact, I can show you that exact Slurm file later. But say you wanted to run this Slurm script, from there, if you want to see like if you want to see the progress on that Slurm script, you can always come to jobs and active jobs, and then you'll see the Slurm job that you've submitted, like hello world in this case, and you can see that it's been completed in like 4 seconds. And you can also see the VS Code jobs that you have running. So going between these two things, uh, first is the account or dash A. Dash A, the account should always be ML at UVA because that's the allocation that you're going to be running. Unless you're working under your own professor, in which case the allocation would be different. But that's like in, for example, one of my professors has an allocation called SpinQuest. So that would be like sbatch dash A SpinQuest instead of ML at UVA. And then the next part is partition equals GPU or dash P GPU. That should always stay the same. That just means that you're like partitioning for a GPU and you're waiting in a queue to submit this job. Uh, that should not be changed. Next is the sbatch gress equals GPU1. Gress simply stands for generic resources, and GPU1 just means that the you can use any one GPU that's most recently available. Since Slurm is a job submitter, these jobs go into a queue, and this queue can sometimes get pretty long based on how many people are currently using Rivanna and how many people want to submit jobs on specific GPUs. But otherwise, uh, Gress GPU1 is the most simple uh, version of this. If you want to use a specific GPU, like for example, an A6000, an A40, a B100, or an A100, you can always just change it to Gress GPU and then like A100 or something like that. Rivanna has two models of A100s. Uh, there's two nodes of like a 40 gigabyte A100 of GPU memory, and there's 18 A100s with 80 gigabytes of memory. So if you want to do like a specific A100, like an A100 with 80 gigabytes, all you have to do is go back to this Slurm script, and then right below the Gress GPU1, you would have like a line that's sbatch and then constraint and then A100 80 gigabytes. From there, the rest is like fairly obvious. CPUs per task is just the number of CPU cores uh, that are being requested here. And the dash T is just time. In this case, I'm setting the time to 10 minutes. And time here means like how much time can this job go on for before it's forcefully canceled. So in this case, I'm saying after 10 minutes, just stop the job, regardless of whether it's finished or not. And then dash J is the job name. So the job name I'm putting is hello world. And the sbatch dash dash output here, this just means where like it for in this case, the hello world.py just prints out hello world. So it'll print it out in stuff.out. So basically the percent %a here is based on the array. Over here, I have sbatch dash dash array 1 dash 2, which means the number of times you should repeat this job. I'm repeating hello world twice, and I'm putting a Slurm array task ID, which is simply the argument that follows from the array. So that means it'll do hello world and then 1 and then hello world and then 2. So it's executing two scripts, Python hello world and then argument 1, Python hello world argument 2. And then the output, the percent %a means it will change the it'll change the file name to stuff_1 or stuff_2 based on which Python file it's executing, like based on the argument here, 1 or 2 from the array. And then the error file is if your Python file has an error, like for example, if I put like hello world.py and then I had a typo in print, then it will instead write to the error file and not the output file. And what it will write to the error file is the traceback. So normally you would get a traceback in like your terminal, but now that traceback and all that, the error in which the line happened, shows up in your .error file. In this case, it would show up in stuff.error. And then this mem1000 is just requesting 1 GB of memory, and the array is just the number of times you're repeating this job. In this case, I'm repeating it twice, 1 to 2. So it's the argument in Slurm array task ID is going to be 1, and then it'll be 2. That's why over here it shows 2 jobs for hello world. In one job, it's using a V100 and it executes that. And then in the other job, it uses an A6000. So in order to run this Slurm script that you have here, you simply type sbatch and then the name of this Slurm file .slurm. So in my case, this is called hello world.slurm. So I would do sbatch hello world.slurm. And I can show you all this stuff soon. To cancel, you would do scancel, and then you can cancel multiple jobs just by putting the job IDs that come from the output. So when you do sbatch filename.slurm, in your terminal, it'll immediately show you job submitted with job ID, and then it'll show you the job ID. So then you can cancel that job based on the job ID, and you can cancel multiple at a time just by separating them by commas. SQ dash U is short for user, and SQ-U with your computing ID here shows you the jobs that are currently in the queue, which you have submitted, but have not started. So this is not particularly that useful because Rivanna has a page or a dropdown here called active jobs, where you can see every single job that you've submitted and whether it's in the queue or whether it's running or whether it's completed. You can kind of see all this stuff here. So it's not all that useful per se, but if you want to use it, you can. And then sbatch dependency after OK simply means that after you submit a job, like sbatch like hello world.slurm, putting another sbatch hello world like sbatch dependency after OK, sbatch hello world.slurm dependency after OK job ID will simply mean that this second job will only start after hello world.slurm has finished. And it can be quite useful if you want to run sequential scripts. Like for example, if you're like training a model, you can train that in one Slurm script, and then you can run your evaluation Slurm file in like another model. Sorry, you can run your evaluation file in like a dependency to evaluate only after the first file like finishes running. So you can also, the first example was hello world. You will most likely never use a Slurm file to run like simple CPU related tasks like hello world. Instead, what you're most likely going to be using it for is for like PyTorch or like training a model and stuff like that. So in my case, this is just a simple file that it's the same GPU loop that just like imports PyTorch and then runs a loop. This loop will go for 10 minutes since I have set the max time to run as 10 minutes, and it will try and allocate an A100 with the constraint of an A100 with 80 GB of GPU memory. And it uses one CPU core, and the rest is kind of the same, aside from like the job name and stuff like that. The different stuff here is the module stuff here. Here, I have module purge, which is just purging all modules. And then I'm loading the modules that I need. So here I'm loading module GCC and OpenMPI. Both of these are like dependency modules, which are needed by needed to load Python 3.11. And then I'm loading MiniForge, which allows me to activate a Conda environment or anything like that. And then I'm loading Apptainer, which is simply a container. And then I load PyTorch. The reason I load Apptainer and then PyTorch is because if you go into Rivanna and if you try to do like module spider PyTorch 2.4, you'll notice that it'll say that one of the dependencies is Apptainer. And then over here, it has Apptainer run -nv container. You're probably wondering where all of this came from when earlier it was quite simply just a simple terminal execution of Python hello world.py. The reason it's like this can actually be shown quite easily. So if I go into this, and then if I go into ML list, just to make sure I haven't already loaded, okay. So I'm gonna unload Apptainer and PyTorch just to load it again and show you what I mean. But let's start with module ML unload Apptainer 0.3.4 ML unload PyTorch 2.4.0. Now, if I wanted to run a simple script, just like in my terminal with PyTorch, you could certainly do that. Uh, However, if you want to like train a model or something like that, then for starters, you might want to know how you would actually run the script to use the existing PyTorch module. So first you would do ML spider PyTorch, and then you would probably just type PyTorch normally. But in my case, I know the exact version I want, so I'm going to type this. And you'll see that you will need to load Apptainer. It kind of tells you. So you can start by doing that. ML load Apptainer 1.3.4. And then you can do ML load PyTorch 2.4.0. And now, as you can see, it gives you some extra information here. To execute this default application inside the container, you run this, and then you run like your Python script. So that's where I got this from. It tells you if you want to run something like on PyTorch, you need to run it within this container. And if you want to run it within this container, you must have this before your Python script. In this case, GPU loop.py. So you then take that and you put it into your GPU loop.slurm, and it'll execute this this Apptainer, PyTorch, and then GPU loop.py. You can think of everything here as just terminal commands that you might need uh, in order to run your Python file, and then you can start by submitting your job and running it. So in this case, I'm going to demonstrate running Hello World. But before that, I'm going to first start by explaining more in detail what Apptainer really is. So basically, as I've shown you before, if you do module spider PyTorch, you need to load Apptainer, and you can then run your Python script like that. But basically, Apptainer is essentially just a container that kind of contains PyTorch. And there's different Apptainers for like PyTorch and TensorFlow. So if you go into like, if you wanted to load TensorFlow, for example, you need a different Apptainer version. So if you do module avail, or not avail, module spider TensorFlow, and then if I wanted like say TensorFlow 2.1.2.13.0, you'll notice that it's a different app. Yeah, I guess it's the same Apptainer version in this case. But for different like TensorFlow versions, like for example, TensorFlow 2.17, it would most definitely be a different Apptainer version. And these are just containers which hold like TensorFlow and PyTorch and whatnot. So that's kind of that. And then you can also do a Slurm like file with the conda environment. So for example, say that like uh the PyTorch version that's like available through module load is not like doesn't exactly work for the model that you're trying to run. Like say that you need like PyTorch, like say you need a specific PyTorch version, which isn't available through module load. You can always just like kind of make a conda environment and you can do like you can you can always like manually just like pip install temp like PyTorch and everything else that you might need through that. And then if you wanted to load your conda environment within a Slurm script, you can do module purge, module load mini forge, and then you can do source activate instead of conda activate, and then your path to your conda environment. And then you can run your Python script. So that is just another simple way to like just activate a conda environment and get your model running. But for now, I'll just demonstrate like uh a quick and simple Slurm file. So hello world.py is it just throws your error into stuff.error and it'll throw your output into stuff a.out. My hello world.py has like the sys argument task ID, which comes from the Slurm array task ID over here. The way this executes is it'll show like Python hello world 1 and Python hello world 2 in your terminal. So what you would type here is, well, first I have to make sure I'm in the right directory, which I am. So from here, you can do sbatch hello world.slurm, and it submitted the batch job, which you can again go check over here in jobs, and it's being queued. I said that I'm in the GPU gress part. I put one, which means it'll use any GPU that's available. These are the GPUs available, and it'll just choose one and run it. Oh, I guess it's done. So from here, you can see your output in stuff one and stuff two, which is hello world from one and hello world from two, which is what I've printed in my Python file. You can also kind of do the same thing with GPU loop and a Slurm file from there. And you can do the same thing with your like conda example. But yeah, do you guys have any questions so far?
There any like modules that aren't on like ML avail? Like let's say I wanted to like use some different like mid processing library or use like a Hugging Face online data set or something. Would that be available
No.
through no?
So like for example, even something like Torch Vision, I don't believe it's available on module load, right? So
Mhm.
if you wanted to get that, you would simply have to make a conda environment and then put your stuff in there.
So if you use the con environment, then you can basically then but using the modules themselves, you can't do everything.
Sorry, say that again.
So like if you use a conda environment, you can basically do anything with specific like packages and modules, but you can't do that
Yeah, pretty
dependency.
much. You can
Okay.
submit any job you like. The conda environment is more like uh versatile and yeah.